Okay, so I want to take a look at a couple of the formulas that we were dealing with last class. We know we know from a couple classes ago that we were dealing with all the mv plus mv equals mv plus mv, all that sort of stuff. That was all law conservation of momentum. But to kind of see how last class fit in with everything else, I want to take a look at the two new formulas that we saw. I don't want to say two new formulas. They're pretty much the same thing, except they're slightly differently rearranged for us. All right. So remember the original formula that we looked at was P equals mv. Remember, P stood for momentum, m for mass, v for velocity. So as long as we've got a mass and we've got a velocity, we can figure out what a momentum is for a particular problem. Now, for the most part, we just use the MV portion of this, right? That's when we were setting up the different types of collisions. So we have three different types of collisions. One of them is elastic, and it would look like this, where I would have one object, and then I would have another object, and then to end with, these two objects would have done something. We could have bounced off each other or knocked into each other in some way, but I still would have ended up with two objects to end with. In other words, they wouldn't have stuck together or anything like that. And this would have been an mv plus mv equals mv plus mv equation, right? So the law of conservation of momentum tells me that these momenta to begin with would have to be the same as the momenta to end with. If I'm dealing with an inelastic collision, we already know what it is, even though we haven't really used these terms so much. Remember the one day I had you write them in and I said, oh, we're not going to really worry about them quite yet, but later on it'll make more sense. This is that later on. So why is this called an elastic? Oh, because it's this bouncy collision, right? We have a couple of objects that knock into each other and then they bounce off each other. So I like to think of elastic collisions as bouncy collisions. I think that helps out a little bit, at least in my mind. All right, so for inelastic collisions, you can think of them as pretty much the opposite, right? If I'm not going to have a couple of objects knock into each other and still have a couple objects to end with, what's going to end up happening is I'll have two objects to begin with, and then I'll have still two objects, but in terms of actually thinking about it as a momentum problem, we would just say that those two objects move together as one. So for our purposes, they really are pretty much like one object because they've become stuck together in some way. So a sort of a bad example of this, but an example that we can talk about would be getting into a rear-end collision. One car ends up smacking into the back of another, and if their bumpers get entangled in any way, now they're going to end up sliding as one big mass. Hopefully not anything that you have personal experience with. And we know that this would be an mv plus mv equals mv, right? And we know that this mass here and this mass over here, those would have to add in order to get what our final mass is. And hopefully that makes sense. It's like, well, in the real world, let's just forget about physics for a second and think common sense. If I have this object and this object, when they go together, now they're going to be whatever the mass of those individual objects was. When we put it into physics terms, it's like, oh, well, this has a mass, this has a mass. Together, they've got a mass that's equal to what they were individually before. And I kind of think of these collisions as sticky collisions, because we've actually had two objects that somehow stuck together. Right, well, an explosion, I know normally we wouldn't think of that as being a collision, but really in the momentum unit, we look at it as another type of collision. And explosion sounds like what it is, so it's not like bouncy, sticky, or anything like that. It's just like, it's an explosion. It's pretty much the opposite of an inelastic collision. So I would have a couple of objects to begin with. They'd be stuck together, and then something would happen where it would cause these objects to split apart. So I'd have one object and another object there then. So this would be mv equals mv plus mv. And we saw some examples of that as well. Okay, so it's kind of a review to see where we're at and what we'll need to be able to do by test time. So now I want to focus a little bit more on just this equation by itself, along with the other two equations that we started to look at. So you might be thinking, well, how did all this stuff fit in with what we were looking at last time with car accidents, car collisions, and the new formula? I equals ft, as well as our other formula for momentum, which was ft equals m change in v. And remember that change is a big deal because we're not just looking for one velocity, we're looking for a change in velocity. So we have to have two velocities in order to get that change. Remember this, what this change in velocity means is actually we're dealing with a v final minus a v initial when looking at this change in velocity. And we could actually rewrite this formula a little bit differently as well, which I'll do here momentarily. Okay, so what is the difference between these three formulas? They all are related to momentum, right? But this one is specifically momentum equals a mass times a velocity, so this tells me what the momentum of an object is that's moving, but how do I get an object to move? I give it a force, and it's more than giving it a force. I also have to apply that force for a certain amount of time in order to get it to move. And that's what the concept of impulse is, like we were learning last class. The impulse for an object is going to be the same no matter what for that specific object. So let's say, for example, I have this object here, and I want to get it to move. Well, I'm going to have the same impulse no matter what I do in order to get this object to move. But of course, there's a couple ways that I can have that impulse. I can either have a really big force in a small time, and that will get this object to move at the same rate, with the same momentum, I should say, as if I had a really small force but a really large time. And that's what I want, right? This example here, that would be normal everyday driving if I'm in a car, right? It takes me a fairly long amount of time in order to make a stop. I wouldn't want to just slam on my brakes, and the whole reason I don't want to slam on my brakes is because I want to increase this time as much as possible so I don't have that much force acting on me. In a car collision, that would be this formula right here. Same formula, I should say, but this particular sense of the formula. I would have a very large force in a small amount of time, right? It doesn't take me much time to change my motion in a car accident because I'm stopping very quickly if I end up getting hit by another car. So we don't want this, if at all possible. We want this. And really, automobile safety is all about how can I make time the absolute longest in order to be able to reduce that force. Okay? So that's impulse. I need a force, I need a time in order to have an impulse. And again, to have an impulse means I'm going to end up changing my momentum. And we can see over here, I can actually even take this ft that's right here. So in other words, I could, anywhere where I see ft, I could put I, right? I, or impulse, is going to be the thing that causes my momentum to change. Okay, so let's take a look at this last formula then. That's where we're going to kind of camp out for a little bit here, just for a moment. So what this last formula shows us is that I need an impulse in order to change my object's state of motion. In order to change the velocity of an object, I need to have this impulse over here, or this force, and this time. Okay, so now let's go ahead and take a look at some of these graphs on pages 9, 10, and 11. The main thing, or actually, 10, 11, 12, the main thing that I want to take a look at right now is the explosions. I'm going to go through that one with you guys together, have you work on pages 11 and 12 a little bit, and then we'll get back together and actually go over pages 11 to 12 and make sure that you feel really comfortable with them. Okay? Okay, so this is the graph that you'll see on page 10. Right, it has to do with explosions. I wish the heading actually wasn't here so that you could just kind of figure out what it is on your own, but it is, and that's okay. So to begin with, the first question asks us to describe the motion of the carts before the collision. And even though it seems a little bit daunting at first, like what the heck's going on with this? You've got lines all over the place. I can figure out what this means, right? Describing the motion of the carts before the collision. I can even figure out where the collision is without knowing too much about this graph. So let's take a look at how to do that. Okay, so to begin with, this, and I shaded in the lines here to talk about them as the red and blue line rather than cart 1 and 2. I think that gets a little confusing. So you may want to do something similar on your own page if you have some colors, or go ahead and use some of the colored pencils over in the corner. You guys know where all that stuff is. Alright, so let's take a look at the state of motion then. Okay, so to begin with, this is my time, kind of a bad axis here, but we can see time of 0 seconds, 2 seconds, 4 seconds, 6, 8, 10, 12. Alright, so to begin with, zeros on this line. So it looks like, to begin with, both my carts are at rest, right? They're both at 0. So 0 means specifically that they're just sitting there. They're just sitting still. So just because I'm moving this way doesn't mean my carts are moving. It means time is moving, right? So it looks like my cars are sitting there here. They're still just sitting there, still just sitting there, still just sitting there, all the way up until this point. At this point, something happens, right? And we know what that something is based on the title of the graph. But the reason I know that this is an explosion is because now all of a sudden, instead of having one object here, and it's not literally one object, it's two carts that are being held together, but instead of having this one mass just sitting there, now all of a sudden one of my masses goes in one direction, goes in the positive direction, because remember, positive versus negative in velocity doesn't mean speeding up or slowing down. It means that I'm either in one direction or the other direction. So one person could think of this top direction as positive and the bottom as negative, if that's okay. Another person could think of it as this top direction happens to be left and the bottom one happens to be right. And yet another person could say, well, I want the top direction to be right and the bottom direction to be left. It's all personal preference, but just realize that the negative means opposite direction. And I know we've talked about that a bunch, but it's always good to have another reminder. All right, so let's take a look at, at what's going on afterwards. All right, so I know at this point something happened to cause one of my carts to go one direction, the other cart to go a different direction. Well, now that they're traveling at different directions, after they're done with the actual change in their movement, and this would actually be the impulse, we'll talk about that a little bit more in a second, but now all of a sudden it's back at a constant velocity here and another constant velocity here. We could actually tell what's happening after the collision as well. To begin with, they're sitting still, and then after, one of our carts seems like it's going fairly slow. The other cart seems like it's going fairly fast, and we can tell that based on the comparison of the two lines. All right. So based on the velocities before and after the collision, how does the mass of cart 1 compare to that of cart 2? At first, that doesn't seem like a whole lot of sense. I mean, how the heck am I supposed to figure out what the mass of these cars is when I'm only given a velocity and a time? I don't know anything about my mass, or at least it doesn't seem like I do at first glance. But actually I do. Just take a second to think, how could I figure out what my mass is based on this graph? If you need some help, we got a hint. Right? We know that we've got a formula for momentum. Momentum equals mass times velocity. Well, I know that this is talking about momentum because I do have a velocity and I do have some carts moving. So these have masses. We don't know what the masses are, but they have movement, so they must have some sort of momentum. Alright, so if you haven't figured it out, here's how we can actually figure out what the mass is. Or at least get a ballpark estimate of what the mass is. I'm not going to be able to tell exactly, but in comparison from one cart to the next, I'll be able to tell which one is the more massive one, which one's the less massive one. And here's how. Alright, so I know from here to here, my velocity doesn't seem to change that much. All right, let me just extend this line out so we can see what we're talking about. And I'm going to extend this line out as well. So we're looking for the change from here to where the original position was, or the original velocity was. So what does this tell me? Well, what it tells me is I have some sort of change in velocity. By itself, it really doesn't tell me much. But when I compare it to my other line down here, if I go from the middle again to the bottom, here to here, again doesn't tell me very much by itself, but in comparison from here to here, which one had the greater change in position, or the greater change in velocity? Looks like this one doesn't change very much. This one changes a lot. Use some everyday kind of thoughts here. Forget about the physics for a second. Is it harder, based on life experience, to get a heavy object to move or a more massive object to move? Or is it easier to get a more massive or a heavier object to move? Right, normally we would say, we would think, well, it's going to be easier to get a less massive object to move. Well, this right here, this object, so cart 1, it changes its velocity, it moves more than cart 2. So that means that it must be easier to move. Well, if this is easier to move, it means that it must be less massive. So there's kind of a little summary of what our thought should be there. If the velocity of the cart changes a lot in comparison to our other cart, which doesn't change that much, then that means that it must be fairly easy to move, or easy to change velocity. And then think, this is more like a common sense kind of part. If it's easier to move, it must have had a smaller mass. So then let's get back into the physics thoughts then. So large change in motion means that I must have a smaller value for mass. Here's a large change in motion, so I must have a small m there. So for number 2 there, based on the velocities of the before and after collision, how does the mass of cart 1 compare to the mass of cart 2? Now, cart 1 has less mass, cart 2 has more mass. Another way that you can think about this is pretty much the reverse. Right? For cart 2, we can say that the velocity of that cart didn't change very much, right? It's at 0 to begin with, now it's at 2. Now the other one had an increase of 4 meters per second. It's weird at first. Why did I say increase? I didn't misspeak. It's an increase in velocity, but it's an increase in the negative direction. And so this cart here is speeding up more than this cart there. It just happens to be in the opposite direction. All right, so back to cart 2. So the velocity didn't change that much. Well, that means it must have been hard to get this thing to move. Think about more like a common sense aspect now. If it's hard to get something to move, it's going to be pretty heavy. Instead of saying it's pretty heavy, let's get back into physics speak, we'd say it has a larger mass. And if it doesn't have that much of a change in motion, to kind of summarize things up, it means that we must have a greater value for our mass, or a bigger m. So we'd be able to say the reverse is true as well, right? If we didn't want to think about this cart, we could say, oh, well, this cart is more massive because it doesn't move as much as our other cart. All right, so the next one, what time does the collision take place? I'm not so concerned that you can tell me the exact time, because these axes, they're not great. We gotta fix this. But I'm more concerned that you can say right at this point, right there, that is where I begin to see a change in motion. All right, so that means this is where my collision starts. All right, where my collision ends would be where my carts have equaled back out in terms of their velocity. So that's where it ends. So if this is the beginning, And that other line that I just drew is the end. Well, this is the time that it actually takes this collision to occur. So here's how that other formula that we learned last class, how it actually ends up fitting into everything, because if if there's a force that causes these to start moving, we don't know how much that force is, right? It doesn't tell us on the graph, but common sense would say, well, I need to have some sort of force in order to get this to move, and now I have a time. This is, see if you can figure it out on your own before I say it. You're what? And hopefully you're thinking, oh, that's my impulse. So that's how our formulas relate to one another. We need an impulse in order to get a change in momentum, in order to go from, in this case, something that doesn't really have a momentum to something that now does have some sort of momentum. Right? We can't say what the exact momentum is over here. To begin with, we can say it's 0 for sure, because it doesn't matter what my mass is, because it's m times v. Well, v 0. My mass can be 1,000,000,000, it could be 1, it could be 10. Doesn't matter what it is. It's going to be multiplied by 0 velocity, so my momentum overall is going to be 0. So this impulse causes my momentum to change, which is why we can come up with that other formula. That impulse, which is the same thing as Ft, is the thing that's going to cause, or is going to be equal to, my mass times my change in velocity. Of course, this formula relates these two other formulas together. So we can actually say something more about the mass rather than just this cart seems to be more massive than this cart based on our logic. We can actually say how many more times massive it is based on the change of speed. Right? This cart, it moves half the distance, or it has half the change in velocity, I should say, as this cart. So what does that mean for our mass? Kind of think about that on your own here for a second. Alright, so what that means is that cart 2 is actually twice as massive as cart 1. Hopefully you see why that is. So if this cart was twice as hard to move, and we know it's twice as hard to move because its velocity changed half as much as the other cart, that means that it must have been 2 times harder to move, so it has 2 times as much mass. The other way to think about that, kind of like what's going on down here, is that cart 1 is twice as easy to move. So this cart right here, it's twice as easy to move in comparison to our other cart. So its velocity changes twice as much. That means it must be 2 times less heavy, or half as heavy. So there's 2 ways to get to the same answer. So that's a lot of information to throw at you. You probably need to watch this a couple of times, go through it a few times, talk it out between each other before the test. Okay. So you should be able to use this, and hopefully you filled this out in your notes as you were going along here. You should be able to use this to help you out with the other 2 pages. And then there's another video that goes over the answers to those 2 pages. It won't be as long as this one, because this is the one that you're learning this for the first time, but it will it'll help explain everything that's going on. I did just realize I forgot, after the collision, the velocity of cart 1 does what? Well, cart 1 is this guy down here. So this is the last question on that page. Kind of alluded to it before. It's that it actually increases. There's a lot of people that want to say it decreases. If I'm going from, maybe this was 4 and this was 0, then that would be correct, but I'm not. It's 0 to begin with, and then it's -4. Mathematically, going from 0 to a negative does mean that we're decreasing mathematically, but remember, the negative here is a conceptual thing. It means that we're increasing our speed, going from 0 to 4. Now let's look at the negative. What does the negative mean? Oh, in the opposite direction. So I'm increasing in the opposite direction from the other cart. Okay? So again, go ahead and give this a shot, and then we'll get back together in a little bit, and you can go over the rest of the answers then.